Welcome back to Mathematical Analysis. In our last lecture, we established the real numbers as an ordered field using axioms. But there's something we haven't addressed yet. Before we talk about all real numbers, shouldn't we talk about the simplest ones? The integers, 1, 2, 3, and the fractions, 1/2, 3/4. Today, we're going to build these number systems rigorously from the ground up, and you'll discover that even something as simple as counting has deep mathematical structure. Let's start with section 1.6, the positive integers. Here's a question that seems trivial. What is an integer? The obvious answer is just to list them. 1, 2, 3, 4, 5, and so on. But Apostol does something strange. He doesn't just list them. He defines them using what he calls an inductive set. Why does he need this formal machinery just to count? Let's break it down. Definition 1.3 introduces the concept of an inductive set. A set S is called inductive if it satisfies two rules. Rule A, the number 1 is automatically a member of the set. Rule B, if any number x is a member, then x plus 1 is also a member. That's it. Two simple rules. Let me give you an analogy. Imagine a club with strict membership rules. Rule A says the number 1 is automatically in the club. Rule B says if you're in the club, your neighbor, x plus 1, is also in the club. This is an inductive set. Think of it like a row of dominoes. Rule A is pushing the first domino. Rule B says every domino hits the next one. If both rules hold, then all the dominoes fall. The entire sequence is determined. Now here's the insight. The set of all real numbers, capital R, is an inductive set. It contains 1, and if it contains x, it contains x plus 1. But the reals have too much junk in them. They contain fractions like 1/2 and 3/4. They contain irrationals like the square root of 2 and pi. We want to isolate just the pure counting numbers, just the dominoes, nothing else. So Apostol defines the positive integers, capital Z with a plus sign, as the intersection of every possible inductive set. What does this mean? It's the smallest possible set that obeys the two rules. By taking the intersection, we strip away the fractions, we strip away the irrationals, and we're left with only the pure counting numbers, 1, 2, 3, 4, 5, and so on. This definition is not just pedantic formalism, it's the bedrock of mathematical induction, which we use to prove almost everything in number theory and analysis. This is why the definition matters. Mathematical induction works precisely because the positive integers are the smallest inductive set. When you prove a base case and an inductive step, you're leveraging the exact structure of definition 1.3. The dominoes must all fall, because that's what defines them as dominoes in the first place. This circular-sounding logic is actually perfectly rigorous when you understand the underlying definition. Now that we have integers, we can study their internal structure. Section 1.7 addresses one of the most fundamental questions in mathematics. Can we break integers into smaller pieces? And if so, is there a unique way to do it? Theorem 1.9 is arguably the most famous theorem in basic mathematics. It's called the Fundamental Theorem of Arithmetic, or the unique prime factorization theorem. It states that every integer greater than 1 is either a prime number, or it can be written as a product of prime numbers. And crucially, this factorization is unique. No matter how you break down the number, you'll always get the same primes. Think of this as the chemistry of mathematics. In chemistry, every molecule is made of atoms. You can take water, H2O, and break it down into 2 hydrogen atoms and 1 oxygen atom. In mathematics, integers are the molecules, and prime numbers are the atoms. They're the indivisible building blocks. Let's take the number 12. You can break it into 4 times 3, but 4 isn't prime. 4 itself splits into 2 times 2, so 12 equals 2 times 2 times 3. You cannot break it down any further. 2, 2, and 3 are all prime. They're atomic. You've reached the fundamental building blocks. And here's the uniqueness part. The chemical formula for 12 is fixed. No matter how you smash the number 12, you will always get 2 copies of 2 and 1 copy of 3. You will never get a 5. You will never get 3 copies of 2. The factorization is unique. This seems obvious, almost trivial, but proving it rigorously requires some very sophisticated tools. To prove that prime factorization is unique, Apostol uses 2 crucial theorems from section 1.7, Theorem 1.6 and Theorem 1.7. These are technical, but absolutely essential. Let me walk you through them carefully. Theorem 1.6 states that if you have 2 integers, a and b, their greatest common divisor, which we call d, can be written as a linear combination. That means d equals a times x plus b times y, where x and y are some integers. This is deeply non-intuitive. Let me show you with a concrete example. Let's take a equals 4 and b equals 6. What's their greatest common divisor? Both are divisible by 2, so the GCD is 2. Now, the theorem claims we can write 2 as 4 times x plus 6 times y for some integers x and y. Can we actually do this? Let's try. If x equals -1 and y equals 1, then 4 times -1 plus 6 times 1 equals -4 plus 6, which equals 2. It works! We've successfully expressed 2, the greatest common divisor, as a linear combination of 4 and 6. This might seem like a party trick, but it's the foundation for Euclid's lemma. Now, we can state Euclid's lemma, Theorem 1.7. This is the atom smasher. It says, if a prime p divides a product a times b, then p must divide a, or p must divide b, or both. Let me give you an example. If 3 divides the product 6 times 10, which is 60, then 3 must divide either 6 or 10. In this case, 3 divides 6. The prime cannot magically appear in the product without being present in one of the factors. Here's an analogy. Imagine a prime p is a special type of paint, say red paint. If you discover that a product a times b is painted red, meaning it's divisible by p, then either a was red or b was red. You can't create redness by multiplying two non-red numbers. Primeness cannot spontaneously emerge from non-prime factors. This property is what makes primes truly atomic. And this is the hammer we use to prove that factorization is unique. Here's the logic. Suppose for contradiction that 12 had two different prime factorizations. Pick any prime from the first factorization, say 2. Since 2 divides 12, by Euclid's lemma, 2 must divide at least one of the primes in the second factorization. But primes are only divisible by themselves and 1. So the only way 2 can divide a prime is if that prime is 2. Therefore, the second factorization must also contain 2. Repeat this argument for every prime in the first factorization, and you conclude the two factorizations must be identical. Uniqueness is proven. Finally, in section 1.8, we use integers to build the rational numbers, denoted capital Q. The rationals are all quotients of integers. Things like 1/2, -7/5, 3/4, 22/7. Any fraction where the numerator and denominator are integers and the denominator is not 0. The rationals satisfy all the field axioms. They satisfy all the order axioms. So here's a natural question. What's the difference between the rationals and the reals? They seem to have the same algebraic and ordering structure. Are they essentially the same thing? The rationals have a special property called density. Apostol notes that between any two rational numbers, there are infinitely many rational numbers. No matter how close together you pick two fractions, you can always find another fraction squeezed in between them. How do we know there's always a rational in between? Just take the average. If you have R1 and R2, then R1 plus R2 divided by 2 is exactly halfway between them. And the average of two fractions is another fraction, so it's rational. And you can do this forever. Find a number in between, then find a number between that one and the original, then repeat. There's no end. This creates a dense fog of numbers. No matter how much you zoom in on the number line, you will always hit rational numbers. They're everywhere. Between 0 and 1, there are infinitely many fractions. Between 0.5 and 0.6, infinitely many more. Between 0.55 and 0.56, infinitely many more. The rationals seem to fill the entire number line. It looks like a solid, continuous line. But here's the cliffhanger. Despite being infinitely dense, the rational number line is full of holes. There are gaps that no fraction can ever fill. Numbers that exist, that we can point to geometrically, but that cannot be expressed as a ratio of integers. For example, the square root of 2, pi, the number e. These are not rational. They cannot be written as fractions, but they clearly exist. So how do we prove they exist? How do we rigorously fill in the gaps? That's where the completeness axiom comes in. Let's recap what we've built in this lecture. We rigorously defined the positive integers using inductive sets. We proved the fundamental theorem of arithmetic. Every integer has a unique prime factorization. We constructed the rational numbers and discovered they're infinitely dense. But we also discovered they're not enough. In the next video, we'll tackle the most profound concept in Chapter 1. We'll prove that the square root of 2 is not rational. Then we'll introduce the completeness axiom, Axiom 10, which fills in all the gaps and creates the continuous real number line. This is the axiom that separates the rationals from the reals. It's the most difficult, most beautiful, and most important concept in all of real analysis. If you're enjoying this series, please like and subscribe, and let me know in the comments which topics you'd like me to cover next. Thanks for watching!